Let's take a look at this problem. We have real numbers x, y, and z such that both the sum and the sum of squares are equal to 1. Find the minimum value of the sum of cubes. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. First, I'm going to establish some simple bounds on x, y, and z. So from the second equation, I can say that each of x squared, y squared, and z squared is between 0 and 1. And so from this, I can say that each of x, y, and z is between -1 and 1. Then I'm going to do some algebra on the two equations provided, sum equals 1 and sum of squares equal to 1. If I square both sides of the first equation, which means x plus y plus z all squared equals to 1, then this expression will then be comparable with the second equation because the degree of both left-hand sides of both equations are 2. So by subtracting and removing the coefficients, we'll have x plus yz plus x plus xz equals 0. Now from this, at least one of xy, yz, and xz is so-called non-positive because the sum of these three terms is 0. And from this, we know that at least one of x, y, and z has to be non-positive, so that, say, the product xy can be non-positive. Then by symmetry, I'm going to assume x to be the unknown that is non-positive. Then from this, I can say that y equals 1 minus x minus z, and I'm going to split them in this way, so that 1 minus z must be non-negative because z is at most 1, and because x is non-positive, so minus x is non-negative, and so I can say that y is a non-negative number. And similarly, I can draw the same conclusion for z. Next, I'm going to do some algebra on our required expression, which is the sum of cubes. So x cubed plus y cubed plus z cubed, under our assumption that x is the possibly negative number, I'm going to write things in terms of x. To do this, I'm going to factorize y cubed plus z cubed. So I have sum y plus z and y squared minus yz plus z squared. Then y plus z becomes 1 minus x, while for y squared minus yz plus z squared, I'm going to split the squares into the following. I'm going to take out minus half from y squared, so I will have minus half y squared plus 3 halves of y squared. Do the similar thing on z squared, minus half plus 3 halves, and then minus yz. The reason that I'm doing this is that I want the minus half squares, these terms, to combine with the last term, minus yz, into a perfect squared. As you can see, the green terms will become minus half of y plus z all squared, so that I will have 1 minus x eventually. And for the 3 halves of y squared and z squared, that can become 1 minus x squared because sum of squares equal to 1 as well. I'm taking out the 1/2, and then we have 3 times 1 minus x squared minus 1 minus x all squared. So 3 minus 3x squared minus 1 plus 2x minus x squared. So more algebra. And simplifying, I'm going to get 3x cubed minus 3x squared, and then plus 1. So that is what x cubed plus y cubed plus z cubed can become when I write in terms of one single variable. Now at this point, because I'm going to find the minimum, so I'm going to cheat a bit. I'm going to use calculus. So differentiate it. Equals 9x squared minus 6x. And factorizing, I'm going to get 3x times 3x minus 2, which is actually non-positive for this, and even more non-positive, actually non-negative for this part. Not less than or equal, but less than. Okay, so it actually increases for x to be, not negative, but non-positive within this range. So that means 3x cubed minus 3x squared plus 1 increases when as long as x is not positive. So that means it takes minimum when x takes minimum. So now we can say that, therefore, the required minimum is 3x, not x, but I'm going to take minus 1 because what we have done previously, we got x to be between minus 1 and 1. So minus 1 all cubed minus 3 times minus 1 all squared plus 1. So it's 1. And let's see what happens when x equals minus 1. Say, what will y and z equal to? When x equals minus 1, then x squared equals 1. So we have y plus z to be equal to 2, and y squared plus z squared equals 0. But this is obviously a wrong system, as in it has no solution. So what's the problem over all the steps? And it turns out to be that x cannot be minus 1. So that means the bound that we have done previously is not accurate enough. And the way we can try to improve it is that by going back to our original equation. Now that motivates us to find a more accurate bound for x. Now I can rewrite these equations into y plus z equals 1 minus x, y squared plus z squared equals 1 minus x squared. And for sum of two numbers versus sum of squares of two numbers, I can use this inequality, which is that y squared plus z squared is greater than or equal to y plus z all squared over 2. This is either just by doing difference, or like AMGM or Cauchy-Schwarz inequality, as you wish. And I can replace them by expressions in terms of x, which is 1 minus x squared is at least 1 minus x all squared over 2. then 3x squared minus 2x minus 1 is less than or equal to 0. 3x factorize. So we have x will be between minus 1/3 and 1. So from this constraint, we know that x is at least minus 1/3. Now we go back to our previous steps and see whether we can fix this. I'm going to erase the minus 1, solve the system again. It equals to 4/3, while y squared plus z squared equals 8/9. And by solving, you know that y and z are both equal to 2/3. And so that works. So we can find the minimum from this. Minus 1/3, minus 1/3, and so by simplifying you have, and that is 5/9. So this is our final answer.